It has been 10 years since the Nicoll Highway collapsed, but foreman Hing Yo Piao's body has never been found.
And it left an indelible imprint on Singapore's elite disaster assistance and rescue team.
Singapore is a small city-state in Southeast Asia with a booming economy, technology, and beautiful infrastructure. The National University of Singapore hosts one of the top civil engineering faculty in the world, and the country has some of the best civil engineers and researchers, which makes this event that I'm going to talk about rather unfortunate. On the 20th of April 2004, Singapore witnessed a catastrophic engineering failure that shook the nation. During the construction of a subway line, an 80-meter long and 30 meters deep excavation section completely collapsed. The resulting crater was as deep as 15 meters and was more than 100 meters in diameter. 6 lanes of an adjacent Nicoll Highway subsided by as much as 13 meters into the ground. My name is Chido Chashe, and in this video, let's dive deep into the geotechnical engineering failure and the subsequent structural failures that led to the collapse of Project CA24. Welcome to Geotechs with Clemens. A well-renowned Singaporean construction company was awarded a contract to construct a new underground mass rapid transit system on behalf of the Land Transportation Authority. The company adopted the cut-and-cover construction method for the tunnel construction. The method had been used extensively in Singapore to construct subway systems for more than 25 years, meaning that the construction company had good working experience with this method. The excavation was in progress when the collapse occurred. 0.8 meter thick reinforced concrete diaphragm walls had been constructed about 20 meters apart. Prior to bulk excavation, jet grout piling had been installed in 2 horizontal layers at levels 9 and 10 to act as buried strutting and provide strength and stability to the soft soil as the base was being excavated. As excavation advanced, steel struts were installed to support the lateral earth pressure. At the time of the collapse, 9 levels of struts had been installed, and the excavation had reached a depth of about 30 meters. The collapse was so sudden and dramatic that the early press reports headlined, "Gas explosion collapses tunnel." However, the inverse was true, and it was soon discovered that the collapse of the excavation caused a rupture of a gas main under the adjacent road. As for the geologic formation of this site, an aerial photograph from 1969 showed that the site was formed by land reclamations when dredged sand about 3 to 5 meters thick was placed on a shallow seabed over about 30 meters of very soft to soft marine clay with very low shear strength. This geologic formation was a critical contributor to the collapse of the excavation. The main problem that led to the collapse of the tunnel was mainly due to soil shear failure along the marine clay layer, which triggered a domino effect leading to a large wall deflections and buckling of the under-designed supporting struts. You see, in the design of multi-stage and complex excavations, the use of computer software is often required so as to paint a clear picture of the soil structure interaction during and after the excavation process. Before we dive deep into the actual events and the causes of the collapse, it is important to understand a few basic characteristics and mechanisms of soil. You see, the soil strength is heavily governed by the amount of moisture in the void spaces and the ability of that moisture to drain when soil is loaded. So, what do I mean by this? Let's take 2 water-saturated soil samples and subject them to a triaxial shear force. The first sample is sheared in a drained condition, meaning that the build-up pore water pressure is allowed to flow out. The other sample is sheared in an undrained condition, a condition that restricts water from escaping the void spaces. In plotting the stress path on a PQ graph to visualize the stresses experienced by the soil samples during shearing, the stress path of soil sample A, sheared in an undrained setting with no change in soil volume, moves vertically upwards until it reaches the failure line. On the other hand, the stress path of soil sample B progresses towards the failure line at an angle. This is because, as the water escapes the void spaces, a process known as consolidation or soil consolidation, the soil mobilizes shear strength due to the increase in soil particle contacts. In many cases, the drained behavior of soil is critical for excavation works. However, the undrained behavior is still relevant and appropriate for soil with very low permeability. In project CA24, most of the soil supported by the diaphragm wall was soft marine clay that would not drain significantly during the construction works. In the forensic review of the project CA24 disaster, it was discovered that the designers chose to model the undrained soil behavior using the effective stress parameters. That is, they made a cardinal mistake in assuming that the soil would exhibit drained behavior during excavation. Though it's not recommended, it is not uncommon for geotechnical engineers to use this method in design. And here's the reason why. The advantage of this is that the shear strength increase due to the consolidation can be used in the design, resulting in reduced costs when it comes to the construction materials needed. However, the project designers failed to recognize that this increase in soil shear strength is quantitatively wrong, especially for soft clay. Picture this. If we go back to our PQ plot and input the effective strength parameters C and Phi, whereby the shear strength is calculated using the Moore-Coulomb model with an undrained setting. As I described earlier, the soil does not change in volume, resulting in no change in isotropic stress, meaning that the shear stress is resisted entirely by the water in the soil. I want you to notice something here. Drained parameters were used in the model rather than undrained parameters. This resulted in an overestimation of the strength of the clay. The forces and moments in the retaining walls were grossly underestimated, and the deflections predicted were too optimistic. As a consequence, the earth retaining system was under-designed and inadequately sized, compromising the whole project before construction even started. In the aftermath of the collapse, the back analysis of the collapsed wall performed by an independent committee of inquiry revealed that the bending moments and deflections were underestimated by up to 50%. That retaining wall, which was only about 0.8 meters thick, was supposed to be 1.5 meters thick to adequately support the excavation. With the failure of soil and the inadequacies of the retaining wall, it was up to the strutting system to resist the lateral earth pressure and prevent the excavation from caving in, more like the last line of defense. A strutting system is a type of support system for deep excavations that involves installing horizontal beams between vertical walls of the excavation. Strutting systems for deep excavations require careful designs and installation. On a properly designed strutting system, the steel beams, king posts, and the connections should have sufficient load-bearing capacity to carry all the lateral load and prevent the excavation from caving in. In project CA24, there were many inadequacies in the design of the strutting system. For example, there were cases where struts were bearing directly onto the diaphragm wall panels without a waller. The fundamental purpose of a waller is to provide a continuous line support to the retaining wall so that the loads can be redistributed and mitigate the effects of eccentricity and provide the tying effect needed to prevent opening up of the wall joints. When this fundamental was omitted, the effectiveness of the strutting support system was somewhat compromised. The events leading to the collapse were quite revealing. You see, back in February of 2004, just 2 months before the collapse. There had been problems at an adjacent section of the excavation. The contractor discovered that the walla was buckling at the connection with the strut. The joint was retrofitted by welding a C-channel stiffener to the walla beam. This was already a red flag that was not supposed to be ignored. An expert from the Land Transport Authority argued that the computer program had been used incorrectly during the design stage, and as a consequence, the deflections and the bending moments in the walling were underestimated. But guess what? The contractor disagreed with this sentiment. In the early hours of the day of the collapse, similar distresses were observed on a walla of level 8 and level 9, which happened to be the location of the initiation of the collapse. In a last-ditch effort to save the project, a team was mobilized to reinforce the wallas by pouring concrete into the upper half of the edge section. The situation seemed to have stabilized momentarily. However, during the morning, the situation became worse. The distortions on the walla reached a critical state. The workers were instructed to abandon level 9 and start working on level 8. By mid-afternoon, the order was given to evacuate the site. Sadly, it was a little bit too late, and unfortunately, the whole section collapsed, killing 4 workers, including a site manager who had stayed behind to make sure everyone had evacuated safely. His body was never recovered.
10 years may have passed since the Nicoll Highway collapse, but emotions are still raw for construction worker Titicha when he speaks of his former supervisor. The Thai national was one of 8 workers Heng Yao Piao pulled to safety. The 40-year-old did not make it out himself, and his body was never found. In Heng's memory, his former...
So, in conclusion, adopting lower safety standards for temporary works can be costly and deadly, especially for large-scale projects involving complex site conditions. In Singapore, as a result of the Project CA24 incident, temporary construction requires the same safety factors as permanent construction, which is something that I wish could be applied around the world. The work of geotechnical engineers should not only focus on providing safe infrastructure for the public, but it should also focus on the health and safety of the construction workers, so that everyone gets to get back home at the end of each and every working day. I've been your host, Shido Chashe. Please leave a like and subscribe to the channel, and go check out my previous video on geotechnical seismic isolation systems. You have been watching Geotechs with Clemens.